Hexagonal Honeycomb City, a sand and glass megastructure, powered by collaborative innovation. Introduction. The Hexagonal Honeycomb City reimagines urban development as a self-sustaining, resilient, and awe-inspiring megastructure built in desert environments using sand-derived materials, primarily glass and sand-based composites. Inspired by the structural efficiency of beehive honeycombs, the city integrates hexagonal pillars into a domed, interconnected urban ecosystem. By leveraging abundant desert silica sand, advanced glass technologies, and collaborative partnerships with leading companies, this proposal outlines a visionary city that balances stability, sustainability, and human-centric design. The Hexagonal Honeycomb City is a fortress of opportunity, growth, and exploration, harnessing cutting-edge technology to transform arid landscapes into thriving urban oases. This revised proposal incorporates existing companies and projects to drive technological innovation, emphasizing the potential of sand and glass as primary materials. It explores how partnerships with industry leaders in glass manufacturing, renewable energy, robotics, and AI can bring this ambitious vision to life, creating a scalable model for desert urbanization. Design concept. A sand and glass hexagonal honeycomb city. The Hexagonal Honeycomb City is a modular, domed urban framework composed of interconnected hexagonal pillars made from sand-derived glass and composites, arranged in a honeycomb grid. Each pillar is a multifunctional, self-contained unit, supporting homes, offices, services, and transportation networks. The design leverages desert resources, biomimicry, and advanced technologies to create a living city that adapts to its environment. Key design features. 1. Sand-derived hexagonal smart pillars. Material. Pillars are constructed from high-strength structural glass, for example, tempered, laminated, or chemically strengthened, derived from desert silica sand, combined with sand-based geopolymer composites for load-bearing elements. Self-healing glass coatings, inspired by bioengineered polymers, repair microcracks autonomously. Interior. Hollow cores, house maintenance robots, hexabots, energy storage, lithium-ion or solid-state batteries, water filtration systems, reverse osmosis membranes, and waste-to-energy plasma recyclers. Exterior. Aerodynamic breathable glass skins with nanocoatings repel dust, reduce heat transfer, and channel rainwater. Transparent solar glass panels, for example photovoltaic glass, encircle the top, while algae bioreactors embedded in glass walls purify air and produce oxygen. Adaptability. Thermochromic and electrochromic glass adjusts opacity and insulation based on sunlight and temperature, mimicking natural adaptive systems like octopus skin. 2. Honeycomb grid and glass dome. Grid. Pillars form a hexagonal lattice, distributing loads efficiently. Elevated roads, made from glass fiber reinforced composites, connect pillars and support autonomous vehicles and pedestrian paths. Dome. A translucent hexagonal glass dome, reinforced with lightweight graphene or carbon fiber lattices, encloses the city. The dome's smart glass skin optimizes light, heat, and energy, with programmable light displays for cultural events. Theater mode. Scalability. Modular pillars and 3D printed glass components allow horizontal or vertical expansion, adapting to population growth. 3. Homes and infrastructure. MUND. Modular homes. Hexagonal glass pods with shape-shifting interiors, using smart glass and flexible composites, slot into the grid, adapting to residents' needs or weather conditions. Offices and services. Commercial pillars, house offices, healthcare facilities and schools with IoT sensors and AI optimizing resource management. Urban farms. Vertical farms within glass-walled pillars use hydroponics and AI-driven crop optimization, powered by transparent solar glass. 4. Transportation and connectivity. Elevated roads. Glass composite roads support electric vehicles and pedestrian walkways, with hexagonal intersections minimizing congestion. Flying vehicles. Drones and personal air transport, for example eVTOLs, dock at pillar stations, delivering goods and people. Hexabots. Autonomous robots patrol pillar cores and grid tracks, performing maintenance, inspections, and emergency response. 5. Sustainability and biomimicry. Energy. Transparent solar glass and concentrated solar power, CSP-C. Plants generate renewable energy, supplemented by kinetic energy from pedestrian movement. Water. Atmospheric water generators and glass-based rainwater harvesting systems ensure a closed-loop water cycle, with pillars storing and purifying water. Air. Breathable glass skins and algae bioreactors filter pollutants, maintaining clean air under the dome. Waste. Plasma recyclers convert waste into reusable materials or energy, achieving near-zero waste. 6. Safety and resilience. Lighting. Integrated LED systems in glass panels illuminate roads, pillars, and the dome, with adaptive brightness for safety. Weather adaptation. Smart glass adjusts to extreme desert conditions, insulating against heat, venting during cool nights, or sealing during sandstorms. Disaster resistance. The hexagonal lattice and flexible glass composites mitigate seismic or wind stress, with hexabots enabling rapid repairs. Collaborative partnerships, leveraging existing companies and projects. To realize the hexagonal honeycomb city, strategic partnerships with leading companies and research initiatives are essential. These collaborations will drive innovation in sand and glass technologies, renewable energy, robotics, and AI, leveraging desert resources and existing expertise. 1. Glass and sand-based materials. Corning Incorporated. Expertise. Leader in advanced glass technologies, including Gorilla Glass and photovoltaic glass. Contribution. Develop high-strength, self-healing structural glass for pillars and the dome, with nanocoatings for dust repulsion and thermal insulation. Corning's expertise in transparent solar glass can power pillars and homes. Desert advantage. Use locally sourced silica sand to reduce material costs, with Corning's energy-efficient glass production methods. Guardian Glass. Expertise. Specializes in architectural glass, including low emissivity and smart glass solutions. Contribution. Supply thermochromic and electrochromic glass for adaptive pillar skins and dome panels, optimizing energy and comfort in desert conditions. Desert advantage. Guardian's coatings can minimize heat gain, critical for desert environments. University College London, UCL. Desert sand, geopolymers. Expertise. Researching sand-based geopolymer composites as sustainable alternatives to concrete. Contribution. Develop load-bearing pillar bases and road materials using desert sand, reducing reliance on imported cement and enhancing sustainability. Desert advantage. UCL's work leverages abundant local sand, minimizing environmental impact. 2. Renewable energy and solar power. First, solar. Expertise. Leader in thin-film solar panels, optimized for desert environments. Contribution. Integrate transparent photovoltaic glass into pillars and the dome, generating clean energy for city operations. Desert advantage. Desert's high solar irradiance maximizes First Solar's panel efficiency. Bright source energy. Expertise. Develops concentrated solar power, CSP, systems using mirrors to focus sunlight. Contribution. Build CSP plants to power glass manufacturing and city operations, using desert sunlight to melt silica sand efficiently. Desert advantage. CSP thrives in clear, sunny desert conditions, reducing energy costs. Tesla. Expertise. Advanced battery storage, megapack, and solar integration. Contribution. Provide energy storage for pillars, ensuring 24/7 power availability, and integrate solar glass with Tesla's energy management systems. Desert advantage. Tesla's batteries stabilize energy supply in remote desert locations. 3. Robotics and construction. Icon. Build. Expertise. Pioneers in 3D printed construction using concrete and composite materials. Contribution. Adapt 3D printing technology for sand-based geopolymers and glass composites, enabling rapid on-site pillar fabrication. Desert advantage. On-site printing reduces material transport, leveraging local sand. Boston Dynamics. Expertise. Advanced robotics, including agile robots like Spot and Atlas. Contribution. Develop hexabots for maintenance, inspection, and assembly, navigating pillar cores and grid tracks with precision. Desert advantage. Robust robots withstand harsh desert conditions for continuous operation. Skydio. Expertise. Autonomous drones for industrial applications. Contribution. Deploy heavy lift drones for pillar stacking and material transport, enhancing construction efficiency. Desert advantage. Drones operate effectively in open desert spaces, unaffected by ground obstacles. 4. AI and smart systems. XAI. Expertise. Developer of AI systems like Grok for complex problem solving. Contribution. Create Hexamind, a citywide AI to optimize energy, water, traffic, and maintenance, using real-time data from IoT sensors in glass panels. Desert advantage. AI-driven resource management maximizes efficiency in resource-scarce environments. IBM. Expertise. IoT platforms and smart city solutions. Contribution. Deploy IoT sensors and pillars in the dome, feeding data to Hexamind for predictive maintenance and resource allocation. Desert advantage. IoT ensures resilience against extreme desert conditions. 5. Water and waste management. Xylem. Expertise. Advanced water treatment and filtration technologies. Contribution. Supply reverse osmosis and atmospheric water generation systems for pillars, ensuring a closed-loop water cycle. Desert advantage. Xylem solutions address water scarcity, critical for desert cities. TerraCycle. Expertise. Waste recycling and upcycling solutions. Contribution. Develop plasma recyclers for pillars, converting waste into reusable materials or energy. Desert advantage. Minimizes waste transport, supporting self-sufficiency. 6. Biomimicry and sustainability. Ginkgo Bioworks. Expertise. Bioengineering for sustainable materials and systems. Contribution. Engineer algae, bioreactors for air purification and oxygen production, integrated into glass pillar walls. Desert advantage. Bioreactors enhance air quality in enclosed desert environments. Biomimicry Institute. Expertise. Applying nature-inspired design to architecture. Contribution. Consult on biomimetic glass skins, adaptive structures, and honeycomb geometry, ensuring resilience and efficiency. Desert advantage. Biomimicry optimizes performance in harsh climates. Benefits of the sand and glass hexagonal honeycomb city. 1. Structural stability and efficiency. Hexagonal geometry. The honeycomb lattice maximizes strength and minimizes material use, with glass and composites providing high compressive and tensile strength. Sand-based materials. Locally sourced silica. Sand reduces costs and environmental impact, while 3D printing enables rapid, precise construction. Scalability. Modular glass pillars allow expansion, supporting millions in vertical or horizontal configurations. 2. Environmental sustainability. Renewable energy. Transparent solar glass and CSP generate surplus energy, powering the city and glass production sustainably. Water security. Atmospheric water generators and rainwater harvesting ensure resilience in arid deserts. Air quality. Algae bioreactors and breathable glass skins maintain clean air under the dome. Zero waste. Plasma recyclers create a circular economy, minimizing landfill use. 3. Resilience and adaptability. Desert adaptation. Smart glass and composites insulate against extreme heat, cold, and sandstorms, while self-healing coatings extend lifespan. Disaster resistance. Hexagonal lattices and flexible materials mitigate seismic or wind stress, with hexabots enabling rapid repairs. Biomimicry. Glass skins and adaptive structures mimic natural systems, reducing maintenance costs. 4. Convenience and practicality. Integrated systems, pillars. Combine energy, water, waste, and transport functions, streamlining urban services. Smart technology. Hexamind and IoT optimize resource use, enhancing resident experience. Land efficiency. Vertical design preserves desert ecosystems while supporting dense populations. 5. Transportation and distribution. Efficient networks. Glass composite roads and eVTOLs reduce congestion, with hexagonal intersections optimizing flow. Equitable access. Public transport hubs and pillars ensure mobility for all residents. Last mile delivery. Drones and hexabots enable rapid, inclusive service distribution. 6. Social and cultural impact. Community spaces, glass-walled plazas and dome light shows foster cultural engagement and cohesion. Opportunity. Affordable homes and job centers support diverse populations, driving economic growth. Awe-inspiring design. Transparent glass pillars and a luminous dome create a global landmark, attracting tourism and investment. 7. Economic viability, cost efficiency. Local sand and robotic construction reduce material and labor costs, while self-sustaining systems lower operational expenses. Job creation. Partnerships with Corning, Tesla, and others drive industries like glass tech, robotics, and biotech. Global model. Scalable design can be licensed for desert regions worldwide, generating revenue. Implementation strategy. Phase 1. Prototype development. 1. 3 years. Site selection. Identify a desert site, for example, Sahara, Mojave, or Middle East, with abundant silica sand and solar potential. Pillar. Fabrication. Partner with Corning and UCL to produce glass and geopolymer pillars, testing self-healing coatings and solar integration. Robotic assembly. Deploy icon builds, 3D printers, and Skydio drones to construct a 3-6 pillar cluster with Boston Dynamics hexabots for maintenance. Technology integration. Install XAI's Hexamind and IBM's IoT sensors to monitor performance. Phase 2. Pilot city. 4. 7 years. Cluster expansion. Scale to a 100 pillar grid, adding a glass dome with Guardian Glass's smart panels and First Solar's photovoltaics. Resident onboarding. House 1,000. 5,000 residents, testing social and economic dynamics. Performance testing. Monitor sustainability, energy, water, air, and resilience under desert conditions, with BrightSource CSP powering operations. Phase 3. Full city and global replication. 15 years. City completion. Expand to 500 plus pillars supporting 50,000 plus residents with integrated farms, offices, and cultural spaces. Global licensing. Collaborate with governments to replicate in deserts worldwide using local sand and tailored technologies. Continuous innovation. Upgrade with graphene-enhanced glass and advanced AI, maintaining leadership in urban innovation. Challenges and mitigations. 1. Energy-intensive glass production. Mitigation. Use BrightSource CSP for sustainable, desert-based energy with Tesla batteries for storage. 2. Glass brittleness. Mitigation. Leverage. Corning strengthened glass and composite reinforcements with UCL's geopolymers for added durability. 3. Technological scalability. Mitigation. Partner with Icon Build and Skydio to scale 3D printing and drone assembly, accelerating construction. 4. Social acceptance. Mitigation. Engage communities via pilot programs, showcasing affordability and sustainability benefits. 5. Environmental impact. Mitigation. Use local sand and renewable energy with Ginkgo Bioworks bioreactors to offset carbon footprint. Visualizing Hexagon City. Conceptual images can illustrate the city's potential. 1. Glass pillar. Cross-section. A cutaway of a 15-meter glass pillar showcasing Corning's self-healing glass, First Solar's photovoltaic panels, and Ginkgo's bioreactors glowing green. A Boston Dynamics hexabot navigates the core with IBM sensors blinking. 2. Hexagonal cluster mid-construction. Skydio drones stack glass pillars into a honeycomb grid, with Icon Build's 3D printers fabricating components from sand-based composites. Guardian Glass dome panels rise, catching desert sunlight. 3. Sustainable pillar in action. A glass pillar in a sandy desert, its smart glass skin adjusting opacity as bioreactors purify air. Tesla batteries power nearby homes, and a Skydio drone delivers supplies under a translucent dome. These visuals, rendered in silvers, greens, and desert golds, would showcase the city's fusion of technology and nature. Tools like Blender or Midjourney could generate them for investor pitches. Conclusion. The hexagonal honeycomb city, built from sand-derived glass and composites, is a transformative vision for desert urbanization. By harnessing abundant silica sand, solar energy, and partnerships with leaders like Corning, Tesla, xAI, and Icon Build, it creates a self-sustaining, resilient urban ecosystem. This city leverages biomimicry, smart technology, and modular design to address global challenges: urbanization, climate change, and resource scarcity, while inspiring awe as a beacon of innovation. With strategic collaborations, the hexagonal honeycomb city